So welcome all again. So this is the QMM workshop with CCPBioSim, doing QMM on enzyme reactions. I'm Marc, I'm based in Bristol. This is the Bristol student campus, but obviously I'm now, like many people, in my house behind a desk. Let's just really, I'm going to start very basically, but quickly. Enzymes are catalysts, and I presume most of you will know this. They lower the energy reaction, the activation energy of a reaction. So if we have the reaction without the enzyme here, then we can put on the enzyme reaction like this, and the enzyme reaction barrier, which will then come from the enzyme substrate minimum, is going to be lower if it's an actual enzyme than for the reaction without the enzyme. So that's what we're doing, and this kind of enzyme reaction barrier is the type of thing that we can calculate with QMMM. So that is what we're going to do. So you can see actually, you know, an enzyme catalytic cycle, of course, has more processes. One point here is that we can, and I'm sure you know this as sort of chemists, relate the enzyme barrier to the experimental rate, if we look at the free energy barrier at least. Okay, so an enzyme catalytic cycle doesn't only have this chemical conversion step that we will be looking at today, but also the substrate binding and the product release. And I would also always say this really to experimental audiences, that these steps may be quite difficult to dissect experimentally. In fact, they are quite difficult to dissect experimentally, but with computers with computer simulation, this is really quite easy. And you may have already done some workshops today that, for example, look at binding free energies, which is involved in substrate binding, and just the dynamics involved, for example, in binding a substrate and a enzyme substrate complex. But if we want to look at this chemical conversion, then we are at the stage that we really need to go beyond at least standard molecular mechanics techniques that probably most of you, if not all of you, are familiar with from molecular dynamic simulations. So the way we do that is with, or a common way to do that is with a QMMM approach, where we have part of the system treated using a quantum mechanical method, which means that all the electrons are included explicitly. So typically, if we look at an enzyme reaction, that would be the substrate and a few key amino acid residues that are directly involved. So especially the residues that, for example, in this case, an aspartate residue that is a base or in the reaction. So we have that only in a small region, because then the much larger region, the whole enzyme and solvent environment, can be included at the MM level, which is much more computationally efficient. So that is probably fairly familiar. This is the technique that essentially won the Nobel Prize in 2013, or a Nobel Prize season, so I thought I might as well mention that again. And well, this is a review that gives you an overview of some of the things that you can do with QMMM for enzyme reactions. Now, a little bit more into the nitty-gritty then of QMMM. And if you're not a sort of quantum computational chemist, then you might not be familiar with all the letter soup that is involved. But I'm really putting this slide up to make a key, potentially obvious point, but an important one, and that is that if you are keen to get really accurate energies, really accurate structures, then you need to go to higher levels of quantum chemistry, but that will come at a cost. It will come at the cost of speed and, depending on the method, also essentially memory, but speed is the most important one. So to give you brief examples, if we use DFT, so density functional, typical density functional functions for our QM region, then we can do some QMMM molecular dynamic simulations, although the sampling has to be relatively limited, compared to other approaches. If we go to even more accurate sort of ab initio approaches, so this long acronym here, CCSDT parenthesis T, is sort of a gold standard for things like energy barriers that we're interested in now, then you cannot even afford to do optimization at this level. So you typically take a DFT conformation and just an energy minimization, no molecular dynamics, and calculate energies at this level. And then on the other side of the coin, we have semi-empirical quantum mechanical methods and EVB, empirical valence bond, with which we can much more easily do quite extensive sampling. And that can be very beneficial because there are many enzyme substrate conformations possible, slight differences, enzyme substrate conformations possible, so we'd like to be able to sample that. Okay, so EVB is really a different kind of method. Sometimes that is also called a QMM method, which is understandable, but we don't really have electrons in the same way. So that comes at a different kind of cost, which I'll come to in a moment. So when we have our QMM system, apart from the method, we need to make several other choices, such as what is the size of the QM region that we're going to use, which is very much linked also, again, the larger the region we want to include quantum mechanically, the more computational cost it's going to be. And then we have other questions as well, such as how do we couple this? And also on the MM side, there are questions of how we treat the MM atoms, which force field to use, periodic boundaries or not, etc., etc. Your normal set of choices there. So a few things that I often stress is that apart from just wanting the best accuracy or the most sampling, we can also think about what's actually easy to use, what you can actually get on with, which protocols are transferable, and of course what computer resources you have available, and importantly, how much human time is going to be involved in setting up the model. And this is where I'll briefly refer back to EVB. So EVB is an excellent method for lots and lots of sampling. But what it requires is that for each reaction, you will need to parameterize your EVB and make sure that it works properly. And that can cost a long time. So, and this is not something, so I don't normally do EVB, so, but to show I'm not biased, this is a quote from more or less a quote from Lynn Camelin, who is an expert in many computational methods and especially EVB. So she indicates that it will be typically taking 6 months or something to do a proper parameterization of a new reaction. So you need to be invested in that particular reaction to do that. Okay, QMM reaction modeling then. So what we do when we want to model a reaction with a QMM method, we need to overcome this big barrier. So this big barrier, for a typical enzyme, even a fast enzyme, the rate will be once per second or something. So obviously we can't simulate a system with QMM and wait for the reaction to happen. We need to force it, and in order to force that reaction, we need to apply bias along the reaction coordinate. And the reaction coordinate we can define in a number of ways, and we'll use actually the simplest type of thing that we can do, which is a geometric reaction coordinate during the practical. Now, okay, so I'm just conscious, of course, that I'm talking here. Hopefully you can follow it all well. If you do have questions, there will be time for questions after this presentation, but you can also already post them in the chat, and I can see if I can pick that up in the meantime, or one of my demonstrators can pick it up and alert me to it. Okay, now I'd like to mention two key different approaches for QMM reaction modeling that's kind of independent of the method or software that you use, and we'll be using both approaches during the practical. So the first is to calculate a potential energy surface for your reaction, and that is essentially just involving doing a series of QMMM geometry optimizations or energy minimizations. So what we actually do then is we start from a enzyme substrate conformation at a particular starting point, a value of our reaction coordinate. Then we move further along our reaction coordinate and fully energy minimize the conformation that we get. And we do this in small steps, so bit by bit we build up the energy profile. In order to make this a smooth energy profile, occasionally you might have to go back and forth in order to avoid sort of jumps, which would be a jump to essentially a different potential energy surface. So I'll mention this term. So essentially you can draw a line through these, and the nice thing about this way of doing things is that these points are actually the full QMMM energy that you calculate, so the full energy of your system. So it's fairly straightforward to just get these values. So not having jumps in between, that is related to the term I'll bring up now, adiabatic mapping, which is a bit of a Bristol phrase, and I'm bringing it up because in the tutorial information you will see this term coming up. Essentially what it means is that we do a potential energy surface using minimization, and we make sure that we are not jumping from one potential energy surface to another, which would be a sudden discontinuity in this curve. Okay, so then we can also calculate a free energy surface where we would, for example, use QMMM molecular dynamic simulations along the reaction coordinate. Getting the energy profile out is a little bit more involved in this way. So typically you use an enhanced sampling technique like umbrella sampling. And to very briefly outline that, we again take different points along the reaction coordinate, and at each point we again restrain the system to be around that reaction coordinate value. But different from here, where we just really want to fix it effectively at a particular reaction coordinate value, we want to restrain it but allow sampling on either side. So if we do that along several values of the reaction coordinate, then we are building up a set of histograms where we can where this is the value of the reaction coordinate that is sampled with this particular restrained value. So these histograms look a bit like hills, and with a bit of fantasy they look like umbrellas, which is where the umbrella sampling comes from. So what we want to get from sampling like this is we have nicely overlapping umbrellas that you can, as you can see here, because then we can start using some statistical approaches to work out the free energy barrier. I won't go into those into detail. We will be using one of the longest established approaches for the practical, the weighted histogram analysis method. And conceptually how that works is essentially we're going to work out at each point, are we sampling more on the left side or more on the right side of this restraint value. So if you sample more on the left side than on the right side, that means that the gradient in your energy must be like this. I hope you can see that mouse moving. So we can do that for all the umbrellas, and with that we can then start building up essentially an energy profile. So what we eventually get out when we use the weighted histogram analysis method is a free energy profile, which is less directly related to total QMM energies that we have. Okay. Hopefully, so I can't really easily see the chat at the moment, but hopefully there are no urgent burning questions, and I'll move on to explaining the difference briefly between two fundamentally different approaches to do QMMM that are distinguished by calling it the additive approach and the subtractive approach. So the additive approach is an approach that is used in most software, including in Charm and Amber, so the MM packages that have for a long time had the ability to do QMMM, and also in the newer implementations in NAMD and GROMACS and so So the way that works is we really just have the QM energy in the QM region and the MM energy in the MM region, and then a term that describes the interaction between these two regions. That is a contrast with the subtractive approach, which is really known because it is the approach used by Onium in Gaussian, where we have where we take the MM energy of the total system and then add the QM energy of just the QM system and then subtract the MM energy of the QM region. So that relies on this term to be, a reasonable description, which may or may not be easy. Well, may not be so easy to do because that relies on using an MM method for your QM region. In both cases, and this really is almost virtually always the case in any implementation of the additive approach, in Onium you can choose this, and it's now the more standard approach to use. In both cases, it's very important to account for polarization of the QM region by the MM charges. This is really, one of the reasons why we want to do QM in the first place. You don't want it to just be some scaffolding around. You want that electronic influence, and that's called electrostatic embedding. Now, this QMM interaction term, of course, is key for the additive approach, and I won't go through all the terms, but it looks something like this. So we make sure that the MM atoms feel the presence of the QM atoms in terms of electrostatics and also van der Waals, and vice versa. The QM atoms and the electrons essentially should also feel the presence of the MM charges. Okay, so important for the additive approach is that we have a boundary between the QM and the MM region, and often for enzymes of interest we will need to have a covalent bond across this boundary, for example the side chain of an amino acid. Now, this link atom approach here at the top is really by far the most popular approach to solve the issue that we have when we have a boundary across the MM and QM region. And the issue is that we need to satisfy the valence in the QM region. So that is done in the link atom approach by essentially adding typically a hydrogen along the MM-QM boundary bond, so that we have hydrogen there that satisfy the QM region, and the MM atoms feel the forces of this as well if it starts moving. There are other approaches that I won't go into. So this link atom approach, as I said, is really the most popular and also used in Amber. We won't use it in this tutorial today. I'll get to that later. We won't need any link atoms. So if you do need link atoms in your system, the key is to try, if you can, put it on a non-polar bond, so you get least sort of problematic effects from having a link atom there. So typically, if you want to include amino acid side chains, you could put it along the C alpha C beta bond. Okay, I'm putting this slide up. I'm not going to talk to it for a long time. This is not a tutorial on QM methods itself, but it's just to point out again that we have different flavors of quantum mechanics where we can crudely distinguish semi-empirical methods that tend to be fast but can be quite inaccurate, so we need to be aware of that. It can be perfectly inaccurate in energies, as we'll see today, and occasionally also inaccurate in the mechanism if you do more complicated reactions. There are ab initio methods. Hartree-Fock is not great, but if you use approaches to include correlation, then they can really get quite accurate, but also can get really quite slow. And density functional theory tends to be at the cost of Hartree-Fock, more or less, so not super expensive computationally, but can get to the accuracy of sort of better ab initio methods. But one point, of course, is that to make is that these density functional methods are not systematically provable. So even though So, for example, methods like MO62X do really well on benchmarks of reaction barriers, but we cannot be absolutely confident they will always do the right thing. Okay. So before we move to the workshop material, just a brief outline of the things that we can do with QMM reaction modeling. We can help determine mechanisms of reactions by following two alternative ones and see which ones are giving us a much more reasonable energy barrier. You can do things like identifying intermediates and so on, catalytic residues, analyze contributions to catalysis, exploring conformational effects. Can at least already get an atomic level description, and that can sometimes already be very useful just to get insight of what actually is going on. And ultimately all these things have to do with relating the enzyme structure to its activity. And the ones here with arrows are essentially what we will be looking at in the tutorial today as well. Okay, so on then with the tutorial for today, we'll be looking at the enzyme Chorismate mutase. It's a popular choice for QMMM, partly because it's such a nice test system. It has the same mechanism of the reaction in the enzyme in solution as well as in catalytic antibodies. And we don't need any sort of active site residues directly involved in the reaction. So there's no covalent catalysis. So we don't need link atoms in this case. Our QM region can just be the Chorismate. And in the past, this has been an enzyme that's been used a lot also to try and settle debates such as why are enzymes such good catalysts. Okay, so the Chorismate to prefenate reaction is a reaction where a carbon-oxygen bond is broken and a carbon-carbon bond is formed, and it is known that this happens through a transition state that's fairly symmetric. So this bond breaking and bond formation happens more or less at the same time. That's the reaction we'll be looking at, and the system that we'll use for this is the simulation system is set up using some simulation tools that we have been developing over the last few years in the group, called Enlighten, with the more recent stuff sort of visible on this website. And very crudely, this is partly to make this efficient and easy to set up. We will have the enzyme, we have an active site or a ligand bound to the enzyme, and what we really do is, as an approximation for QMMM studies, if you're just interested in the mechanism, this is enough. If you're not looking at large conformational changes, for example, we can fix part of the enzyme that's not near the active site and let the atoms only move in a sphere around there, which helps with efficiency. So here's Chorismate mutase with 3 active sites, and we'll just be focusing on one active site where we have added our solvent layer, water layer around. So if you're interested in this Enlighten methods, then I'll point you to the website and this publication where you know the process is outlined, and I won't go into detail now. It's really for people to get people into simulation if they are not comfortable with actually using the command line or anything, because you can set up your system through a Pymol plugin. But perhaps for people like you, you can also use these Python wrappers that are used to just help yourself automate the processes when you set up a system. So we'll be using this in this case. So this is the bit that I've done before we start with the tutorial. We have Chorismate mutase here in the active site. We do an MM preparation, which means that we get parameters, general Amber force field parameters for the ligand. So in this case, Chorismate, the substrate. And we protonate the active site, etc. So that's done in half a minute in this, using this prep protocol, essentially fully automatically. We just need to indicate the charge of the ligand. Then we can do some quick structural optimization in a few minutes. Then we can do a dynamic simulation, which on a standard CPU, in this case, would take 40 minutes because we're using Sander for 100 picoseconds. And what we do today is pick snapshots from this simulation, so essentially restart files from this simulation, and we take these restart files and feed them directly into a QM-MM molecular dynamics simulation where we do umbrella sampling to calculate free energy profiles. So that is what each of you will be doing. I've got actually, instead of 3 different ones, we've got 20 different ones. So I encourage you to just pick your favorite number between 1 and 20 later on to do your umbrella sampling, which will be the start of the tutorial. So I mentioned before, umbrella sampling happens typically along a reaction coordinate, and in this case we're going to use a geometric reaction coordinate. So here we have the reaction again, and our reaction coordinate, perhaps not surprisingly, will be the difference in distance between the carbon-oxygen bond that is broken and the carbon-carbon bond that is formed. And by defining it this way around, it means that in Chorismate, this will be large and this small, because this is the formed bond. So we go from negative to positive, because in prephenate, this bond is formed and this one isn't. So, so that means that this is large and this is small. Hopefully that's clear. Okay, so the tutorial will involve first using umbrella sampling along this reaction coordinate, and then you can get your own snapshot from your own umbrella sampling to do sort of an adiabatic mapping approach to get a potential energy profile. Having gone through the work to do the QMMM modeling of enzyme reactions workshop today, and hopefully by now most of you will have completed the free energy and potential energy mapping of the enzyme reaction of Chorismate mutase. So just to repeat, this is the reaction that we looked at. We went from Chorismate to prephenate with umbrella sampling, then took a snapshot of the umbrella sampling that was around the transition state. And we did the sampling along the reaction coordinate as defined here, so the transition state is indicated. I'll change it to the laser pointer. And yeah, that's how we started this. And what we got out from the potential energy profiles were these 2 plots. So our potential energy profile, so yours might look a bit different depending on which snapshot you had, is essentially the QMMM total energy along the reaction coordinate values. So we see a typical profile of the substrate, the transition state, and the product. And then we used a little trick to see how much the enzyme environment is contributing. And we did that by essentially taking the geometries that we had analyzed here and throwing away all of the enzyme and recalculating. Now, from this, we can work out what the potential energy barrier is for the reaction. And then from these gas phase reactions, that indicates to us how much stabilization the enzyme environment is giving us. Now, so if we collect this for a whole bunch of snapshots, which we have done previously with a slightly different potential, in this case the AM1 semi-empirical method, then you can see that these 2 things, the enzyme energy barrier and the transition state stabilization, so the difference between the gas phase calculation and the enzyme one, correlate, and they correlate reasonably well. And this is in fact also what has been used in the past at a better level of theory. So this is now going back quite a few years, 2005. And B3 was then still a very, very commonly used DFT method. And with that method, we did essentially the same as we've seen today. So for a bunch of different starting snapshots, they calculated a potential energy profile for the reaction on the same reaction coordinate, and then did these gas phase calculations, and then plotted these, sorry, I'm seeing, okay, yeah, and then plotted the stabilization energy against the energy barrier, and showing an even nicer correlation than I showed you before at the semi-empirical level. And you can actually plot destabilization along the axis as well. So what they could conclude, and this was part of the debate that was then still more active about the action of enzymes, what we can help conclude here is that the efficiency of the reaction in the enzyme is determined by the degree of transition state stabilization in the enzyme. So transition state stabilization is what is really key. So an enzyme, ideally, most enzymes are optimized to best bind, to best accommodate the transition state. Several years later, they did the same thing in solution, because that's actually a more proper comparison than doing anything in a gas phase. So you can do the same thing. If you do the stabilization energy in solution is not zero. So it's better than gas phase. The water molecules can help a little bit as well. But again, that's the circles on the line, and the triangles on this line are from the in-enzyme simulation there. And that still is correlating quite well. You can also use these values, so the actual energy profiles then, and the average over several snapshots, which is important to do, to compare against experiment. So in Chorismate mutase, the reaction in the enzyme in solution is the same. So if this is done at the B3-lip level, we see a reasonable agreement for the enzyme, and at least indeed a much higher energy for in solution. But if you look closely, here the difference is 8 kcal per mole, and here the difference is about 6 kcal per mole. So it might be that we're actually missing something. And that turned out to be true, because again, in the past, it was already realized that in fact, there's something more going on when we look at this solution reaction, because Chorismate prefers to be in a more extended conformation in solution. So there is an energy penalty to be paid to get to this conformation, which is the one they used for the solution simulations as well. This conformation that is much better set up for a reaction. In solution, there is an energy penalty to be paid for that, but the enzyme is already constricting the conformation of Chorismate to this. So catalysis can then be said to be due to a combination of transition state stabilization and conformational effects. And these you can then sort of quantify with various different approaches that I won't go into now. But one key observation to make is that all these effects are, in all probability, also due to the fact that the transition state is so well accommodated in the enzyme active site. So ultimately, this additional contribution is about 1.5 to 3 kcal per mole, depending on what approach you use. So here's a couple of approaches that different approaches that were used in the past. And then if you add that correction to the water barrier that was calculated, then again we get in the right ballpark with the difference of about 8 kcal per mole. So this is the kind of thing you can do. You can actually start looking at what the enzyme contributes. But actually a lot more important usually for understanding a catalyst and perhaps changing it is to understand what different residues contribute. So for that, we also did a calculation during the practical. And that was a calculation where we didn't include this whole side chain. And then, as you can see from these plots here, we also have a much higher energy barrier for the reaction. So it turns out that, at least for this particular snapshot, almost all of the stabilization energy around the transition state is due to this arginine 90 residue, which is not really a surprise given its position if you think about it, because what will happen during the reaction is that more negative charge will build up on this atom. So it's very good to have a positively charged, kind of an almost salt-rich interaction in place here. Okay, so again, this was also done at the B3-lip level already a while ago, and the same approach was then done to look at a bunch of other residues around the active site as well. And again, that indicates that arginine 90 is doing the bulk of the work. So this is the type of thing that we can do here. And then just to highlight some other work on Chorismate mutase. I won't spend too long on this. This is just to point out that this is the first enzyme really for which we try to go to a very high level of accuracy. By we, I mean the group in Bristol. I did this later myself during my PhD for a different enzyme. So you can actually use an approximation at that time for CCSD parenthesis T, which is called standard. And if you do that, then you can get quite close to the enthalpic barrier that you can extract from experiment. Typically, you get a free energy barrier from the rate. So we know also from experiment how much higher that is. And that in this paper was actually done by comparing the potential energy surface to the free energy surface. So that leads you to indicate what the entropic contribution is. And that is essentially what we did during our practical today as well. And probably if you look at your values, you'll get something similar to this. And that was considering that we used really very limited sampling during our tutorial today. Okay, so it is possible to, for some enzyme systems at least, to get sort of a near quantitative calculation of activation barriers by using, for example, this approach of doing entropic contribution on top of a very accurate QM energy. But as I said, often I think relative energies are much more useful to actually guide research. Okay, so a brief advertisement to now quite an old review, but still I think a nice overview of the things that you've heard today, but also a bunch of applications at the time. There are many more recent works as well, and this paper is not a review, but it is Chorismate mutase with a particular approach to get to higher level methods without breaking the computational bank, so to speak. But the other thing about this paper is also that it's got a long introduction that discusses some of the issues that have been discussed in the literature more broadly. So at some point there have been suggestions that you may need to go to very, very large QM regions to get anything accurate. But this paper, as well as several other papers that are discussed in this introduction, show that the QM method, as well as very importantly sampling, can in principle make much larger differences than the size of the QM region. So we may really not need to go to very large QM regions, and these other issues here may be more important. Okay, so it's just a graphical abstract of that paper indicating when we use this projector-based embedding approach, we can actually see the whole variety with DFT methods. If you don't use projector-based embedding, that kind of disappears. So we use these same conformations, and that kind of disappears when we use for a smaller subsystem a higher level ab initio method. Okay, so I won't spend a long time now on this. I will just highlight a few things that are important to plan a QM-MM study if you're interested in doing that soon. So the choice of QM method is important, which may be related, of course, to the chemistry that you're interested in. So transition metals will require a DFT approach and not DFTB. And there may be other limitations for the particular chemistry that you're interested in. The choice of MM force field can also make an influence. The QM region, of course, is important, the partitioning of it as well. And of course, you then, depending on what you're after, what you're interested in, you may want to decide whether you're mostly going to focus on QMM molecular dynamic simulation or QMM minimization, this potential energy profile mapping. For example, if you're really interested in just working out what the exact mechanism is, then this approach, by comparing different reaction mechanisms, might well be more than sufficient. Okay, so one recommendation is that you having a small model system where you can then test whatever method you ended up using, for example, in QMMD against a high-level QM method is something that I would highly recommend. And I will finish this wrap-up with just a little overview of software packages. And this is not an exhaustive list, but I will mention this briefly anyway, as it's something that I think is important when you start thinking about this. So CHARM was the first normal sort of molecular dynamics package that had QMMM capability. So it's had that now for decades. Amber followed fairly soon after. But nowadays we also have NAMD and GROMACS interfaces for QMMM simulations. And even if you want to use polarizable MM force fields, you can, for example, use the Tinker HP code. What I would say is that if I look at what publications come out, and I checked again last night if there were a lot of enzyme reaction simulations, and that's a specific thing, you can do other things with QMMM, but enzyme reaction simulations, I see very few applications from these more recent codes, whereas you see plenty from Amber and CHARM. And if I were to make a recommendation, and also why we use this for the workshop, is that Amber is actually a really nice package to start to do some QMMM simulations of your system, because it is, in comparison to most others, really quite user-friendly. So you wouldn't have to worry about the placement of link atoms exactly. It will do that itself. And as I pointed out during the workshop, you can also change directly from a purely MM restart file to a QMMM molecular dynamic simulation. So there are several QM methods. This is again not a completely exhaustive list built in, semi-empirical ones. By that I mean it's part of the Amber tools set, so you can use them within the standard code. You can also, for all of these packages, interface to other QM programs. The ones in bold here are ones that are free or open source. Of course, there are other options, as already was indicated by some people in the chat, for example, through QM packages. It may be harder to, for example, run what we did today, run QMM molecular dynamics simulations, especially with periodic boundaries, etc., in packages, if it is at all possible. And also, it is not always so well tested, I believe, in my experience, how the MM force field is implemented. So that's something else to look out for. So it has come up a few times, also in questions. If you have a system where you, for example, have a transition metal, then using DFT is useful. You may actually want to use different approaches for potential energy surface calculations. Kamp is one code that you can turn to, which is developed by